Okay, so we will continue with section 2.7. We were talking about the Fourier transform, and our purpose here in this section is to solve a PDE with Fourier transform. So the idea is actually quite similar with what we learned before in the previous chapter. So here you have an ODE or PDE. Let's say we have a PDE, and then what you need to do, you are applying the Fourier transform to both sides with respect to a spatial variable that is that have a range from negative infinity to positive infinity. Then you would, if you have a PDE, then you would get rid of one of the derivatives with respect to one of the variables. So then now you have an ODE. Then you just solve this ODE and you find a solution. Now the solution here would have a variable that is in the frequency variable C, and what you need to do is to use the inverse Fourier transform to find the solution of the PDE. So okay, we are going to look at several examples on this. So our first example on this is the heat equation. So here you have a heat equation on the real line, K U X X equals to 0. X is on the real line, and T, the time, is positive, and you have the initial condition that is fx for any x in R. So this is an initial value problem. It's a Cauchy problem. We actually know the solution, and then if you go back to section 2.1, we already know how to solve this. Now, but here we are going to use a Fourier, the method of a Fourier transform to solve it. So okay, we applying Fourier transform with respect to the variable x. Now x here is the spatial variable with change from negative infinity to positive infinity. We can apply the Fourier transform to it. Okay, so u hat c t is the Fourier transform of u xt. Now then this recall that in this process, you when you we let me just before I get go further. So now if we have the derivative with respect to t, and then if you look at this is the integral that only apply to x. So e I c x dx. So we did nothing with respect to the time variable. So therefore, when you apply the derivative, this actually you can take the derivative inside the integral. So then therefore, what you have here is d is ut. So just now on the other hand, the integral is with this integration is with respect to x. So therefore, according to the previous formula, we have this formula u. If you have a u derivative with respect to x, then this should be I, negative IC u had, so that, and then if you have k order derivative, this power here would be k. If you have k derivative with respect to x. And this power here would correspond to the power of k. All right, so we apply the Fourier transform to both sides of this equation. What we have here is ut hat. Notice that we and then, but the key point is that this uxx becomes negative I c square u hat. Now this equals to 0. So here we use the properties that the Fourier transform of a function, the kth derivative of a function is negative I c k, and the Fourier transform of the original function. Okay, so this comes from here. Now then we have this is for u hat. So this negative become positive. So therefore this become plus. This is negative, and then okay, plus k c square u hat. Now for u hat, this actually is an ODE. It involves only differentiation derivative of t, and then this we all know that the solution of this is ct is some function to be determined. Let's call this a phi or a c, and then e. This is negative. This is an exponential growth function, decay problem. So this is this. Now we need to determine this a, this auxiliary function from the initial conditions. Now, if we apply the Fourier transform to the initial condition, then we have this c 0 equals to f hat. This is the Fourier transform of f. So therefore, if you plug, oh, I forgot a t here. So if I plug t equals to 0 here, then I have this equals to AC. So our solution is at this point is then u hat equals to f hat c times e negative k c square t. So this is now, however, this is the solution in the frequency variable, and so we need to find the original solution. The original solution, the solution to the original equation is then the Fourier, the inverse Fourier transform of u hat ct. And now remember, this is a product of two functions, and then by the convolution property, this becomes the Fourier transform, inverse Fourier transform of f hat c convolution. This is not product, it's the convolution of the inverse Fourier transform of e negative k c square t. Now, the function f mapped to f hat, then by the Fourier transform, then the inverse Fourier transform would make f hat back to f. So therefore you get fx, and then convolutes. Now what is this? For this, you have to go back to look at this formula that we have. It's not in this, in the previous file, video. Then using the by the Gaussian the Gaussian function. That let me see. I still have it here. So we have that the Fourier transform of e negative ax square is square root of pi a e negative square 4a. Now in this case, if you replace 1 over 4a by kt, so that is that if you replace the a by 1 over 4 kt, then you know that the inverse Fourier transform of this term is actually this thing is e to negative x square over 4kt, and this there's a coefficient here that is 1 over square root of 4kt. Let me see whether if yep. All right. Then this then this convolution, if you write it down, it is actually this integral from negative infinity to positive infinity f y e this 1 over square root of 4kt e negative x minus y square over 4kt dy. And if you go back to look at section 2.1, that is exactly the same formula that we obtained in 4.1. I mean 2.1. Okay, so let's look at another example on how to use the Fourier transform to solve a PDE. In this case, we look at the Laplace equation on the upper half plane. So the Laplace equation of the upper half plane is uxx plus uyy equals to 0, where x is r and y is greater than 0, and the boundary condition here is equals to fx, where x is in r. So it is on the boundary here, the function is fx, and on the upper half plane we are solving this function, this equation on the upper half plane. Now, okay, so the first thing we need to think about is what I mean, here we have two variables x and y. Both of them are spatial variable. Which variable we should be applying the Fourier transform with respect to? That is the problem. Now, if we look at the range of x and y, x actually range from negative infinity to positive infinity, and y is greater than 0, range from 0 to infinity. So therefore, in this case, we should apply the Fourier transform with respect to x in this case. So we're applying Fourier transform with respect to respect to x. And then this equation here would become u hat and then this would be negative I C square, and this would be U hat Y Y, and this equals to 0. Now this becomes an ODE for U hat, so that if you write this way, this is a C square U hat equals to 0, and this ODE, we can consider this as ODE with constant coefficients, and then the catalyst equation is this. So therefore lambda equals to positive, negative C. Now, so therefore the solution U hat C Y is some constant, let me call it as A C E negative lambda C Y. No, there's no lambda here. Negative C Y plus B C E positive C Y. Okay. Now, actually, in this problem, I did not mention it, but we should have also assumed that this with the assumption that the U X Y is bounded on this region. Now, if you have U X Y is bounded, then you know that when Y is greater than 0, this term would be unbounded. This term is unbounded when Y is greater Y. I meant to say that, okay, I did not. I meant that when C is positive, this term as Y goes to infinity would go to infinity. So therefore, in order for this U hat, if U is bounded, the U hat would be bounded. So for this to be bounded, then this we need to have this B C equals to 0. Now, if C is less than 0, in order for this term to be bounded, then we need to have A C, because if we go Y goes to infinity, this negative and negative become positive, then this exponent here would go to infinity. So therefore, we need to have this term equals to 0. So this, if you want to write this in a nice form, and that is I can write this, let me use another letter, write this as a function phi C, and then this would be E negative Y absolute value of C. Okay, so this is the solution, is in this form. Now, so this again is a product of two functions. So therefore, okay, so we also need to determine what is phi C. So okay, so we use the same trick, and then C0 is you come back is we applying Fourier transform with respect to x to both of these equations. So we get this equals to F hat C. So therefore, the solution is F hat C E negative Y Y C. All right, so that actually give us that these the we have that the solution here is C x y is then the convolution of the Fourier, the inverse Fourier transform of this function, and this convolution of this of e negative y c. Now these actually this would give you fx. Now it actually follows from an exercise. Actually, it's also in the table that I give previously, that the inverse Fourier transform of this function here is y over pi x square plus y square. And therefore, if you write this down explicitly, this is just the integral from negative infinity up to positive infinity of f tau. I use tau as a variable here now, and then times y x minus tau square plus y square, and the integral is now with respect to tau, and we should also have a pi over here. Now this actually this formula has a name to it. It's a Poisson integral formula, and this function here is called a Poisson kernel. Okay, so I will stop here for the time being, and then I may come back to review this next time. So don't forget to do the homework problem in this section. And then if you have any question, you can come to the beginning of next week's class. I will answer your question with regard to the homework problem in this section. Okay, I will see you next Monday.